Hello again. Please join me in welcoming our next set of speakers, Dr. Pushkar Ghanekar and Jayesh Mistry. Pushkar leads the Frontier AI group within Lilly Small Molecule Discovery, which is a dedicated team focused on developing and deploying advanced AI systems to accelerate the DMTA cycle for early-stage molecular discovery. Pushkar earned his PhD in chemical engineering from Purdue University, where his research focused on advancing a molecular level understanding of materials critical for energy storage and conversion to unravel complex interactions. Jayesh is a dedicated product manager at Reaxys, focusing on chemistry search optimization to enhance user experience. With a strong customer-focused approach, Jayesh brings over a decade of experience as a medicinal and process chemist, primarily in small molecule drug discovery. Before joining Elsevier, Jayesh developed his expertise at Pfizer and Merck. Jayesh holds a Bachelor of Science in Chemistry from Sheffield Hallam University. With that, I'll hand it over to Pushkar for his presentation, AI as your scientific co-pilot, frameworks to maximize serendipity in discovery. Pushkar?
All right. Can you all hear me? Just checking quick. I'll start sharing my screen. It's a pleasure to be here. Thank you so much for the invitation. And I look forward to sharing some of the work that we have been doing at Lilly around using AI methods and also building AI agents for helping connecting tools, processes, and accelerating some of the discovery work that we do in early molecule discovery. Before I go into the details, this talk wouldn't be possible without a big set of team that is working on different aspects of discovery, be it early stage chemistry, biology, but also on the tech side, where folks have contributed to the engineering, software design, and coding, but also on the UI, UX of the products that we are building to the users at the end, which are our chemists and biologists in the discovery teams. Also on the side, since this is a talk that is focused on language models and agents, we wanted to share a couple of links and articles that I have found pretty useful in understanding and learning about this specific area, which is quickly changing, but also quite fascinating and exciting to see how it connects with drug discovery and chemistry. So key ideas that I wanted to share today, talk a little bit more about the Frontier AI group that I'm leading, share reaction informatic tools and applications and how we are using Reaxys at Lilly, and then also share a bit around LLMs and agentic AI that we are being using in our internal discovery projects, but also exploring how they can be used for accelerating the work that we do every day. So what is Frontier AI? We are a small group of scientists, biologists, and more on the in silico side software developers in Lilly, looking at how we can use AI machine learning to accelerate our drug discovery pipelines. We are more focused on modeling experimental processes, so building specialized AI models for sequence and construct design, for reaction development, so understanding what are the relevant conditions that are used for optimizing a given reaction. And then how these specialized AI models, learning from our internal data, can be made easily available through agentic AI systems that I'll be speaking to in a couple of slides, and how we can connect these systems with actual wet lab equipment to get real-time feedback and refine experiments iteratively. So not only are we using AI to predict what set of experiments we want to perform next, we also want to use AI to make it easier for people with non-technical background or people with limited coding experience have the ability of asking questions more seamlessly. And in the end, we want to test these capabilities, translate into real world impact by using it on our internal discovery programs. One of the discovery programs that we have recently started is actually looking at antibiotic discovery. And we are wanting to use that as a capability sandbox to evaluate how these methods can be used to accelerate a critically unmet need and a project which is usually always economically and financially strapped for resources. How AI can help reduce the amount of investment that goes into typical drug discovery timelines. So quick information around reaction informatics at Lilly and how we are thinking about our data and some of the models that we are working on helping do better reaction modeling. So from a reaction informatics standpoint, we are trying to build a platform where you can easily access and query synthetic routes associated with different chemical matters. And we are looking into enabling different aspects of a reaction. So not only from a condition prediction, but also for predicting a one-step synthesis on the product given a set of reactants, but also have a set of multi-step methods like a retrosynthetic planning that we would like to make available so that complex chemicals can be synthesized or at least evaluated much quickly. And in that vision to make it a reality, we are trying to capture data that we generate internally through our ELNs, electronic lab notebooks, in multiple different themes. So not only we are trying to capture the final product, we're also trying to capture the performance, the conditions, and the type of building blocks that are used in this particular electronic lab notebook conception. So internally, we have developed something that we call Synthery, which is synthesis history, where we are harmonizing a lot of the data that is generated across different electronic lab notebooks, where we are able to then process these reaction data points to look at the type of reaction following the reaction ontology framework, where every reaction class is annotated by a known set of reaction ontology number that is globally recognized. And then we are also annotating it by the investigator, the experiment, and the type of reaction that was performed. So the synthesis protocol, the indexing and the molecule ID associated with that building block, but also understanding what was the performance of that reaction. This is made available to different chemists to quickly look up their reaction, but also look up reactions based on different types of chemistries. So you can ask questions around performance of a specific building block for a given chemistry as well. We are now then using this data to build specific models that can help predict the performance of a given reaction. So this is something my group member Nathan has been working on, where we have been trying to use these reaction maps to predict a product for a fairly complicated reaction. And the reason this is of an interest for us is because we are always going to explore reaction spaces which are not heavily precedented. So what we are doing here is we are building a machine learning model that understands molecules as set of graphs. With that graph understanding, it is able to predict the set of disconnections and connections it can make. And based on those predictions, it can recreate a new product based on the set of reactants that you're providing based on the context. And we tried it for two different reactions. So the Diels-Alder cycloaddition, where we tested it for known reactants that form a product which is fairly involved reaction. And if you think about doing a rule-based reaction mapping, it's a fairly complicated process. So we developed a machine learning model that can predict the product based on the pair of reactants that are provided. Similarly, we have been working on group 6 mediated dearomatization reactions, which are, as you can see from this chemical space plot, lie very different compared to your usual Suzuki couplings or any other type of reactions. And even for a reaction that is fairly different, the embeddings of the features that we are learning in this model are able to be understood and help to predict the products for a given set of pair of reactants as well. So what we wanted to demonstrate here is that by having a really good set of features and a good set of encoding of those features, you can fine tune or transfer learn these models on a smaller set of reaction space. Therefore, you can create a more synthetically aware platform that can help you predict not only your main product, but perhaps even your side products for a given set of reaction. And this is a platform that is agnostic to the type of data. And we are trying to slowly build this platform so that you can build a reaction map for different types of reactions or different types of portfolio projects that you may be interested in. And we are trying to scale it up so that this can be called on the fly as you are designing a new parallel synthesis or a reaction development campaign. So with the reaction informatics set, we are also heavily using the tools from Reaxys at Lilly, where we are making it easy for understanding what are the different types of building blocks available for from Lilly to be used in Reaxys. So we worked very closely with the team at Reaxys to enable building blocks from the Lily's internal set to be available on Reaxys that can be then populated or shared for easy querying and access. So if a chemist is searching for a building block and those building blocks are available within the Lilly environment, they are populated and making it easy for the chemist to understand whether they are available internally to them or not. The other one is around enabling these building blocks in the retrosynthetic platform itself. So people in the audience must have used Reaxys retrosynthesis. That is something we use pretty heavily internally as well. But what we are also doing in addition to that is enabling the building block that Lilly uses also for these type of retrosynthetic planning software. So you can be very focused in what type of building blocks you're using to deconstruct a molecule and then further prosecute these type of building blocks and complex molecule pathways. And you can rest assured that the pathways that are predicted in this particular retrosynthetic planning optimization are aware of the building blocks that are available for you. So these are the tools and data sources that we are slowly accumulating and using, and seeing how chemistry alongside with AI can be used for helping predict, but also propose certain new types of chemistries that you could do. That said, a lot of the times the limitation that comes across with these bespoke tools is the contextual understanding or just the domain expertise or the coding knowledge that comes with certain in silico tools. So we are using language models and by extension AI agents to lower the barrier to allow to ask these questions and also connect different data sources and softwares. So we think of language models as co-pilots. And the reason we use that term is because language models, as you must have all used, have a really strong semantic understanding of what the intent of the question is. And then they have a broad knowledge base. They can help you understand all the things from the set of catalysts that are used for coupling Suzuki reactions, for example, to writing a poem about your favorite base. And it's that broad knowledge is something that is helpful as a commodity to be used for connecting disparate data sources. That said, they do make up stuff pretty confidently. So that's what you're calling as hallucination. And we have to be very aggressive in factually correcting them. And also there is a knowledge cutoff and lack of context, especially around chemistry. So what we are doing internally is connecting these language models with the relevant context and also tools to help them be understanding of the chemistry and then allow the users to ask questions to these language models so that they are more focused on asking better questions and doing knowledge search and knowledge exploration instead of figuring out the best way of accessing that data. And one of the reasons we are so interested in doing this now is because of the path at which the rate at which the AI is progressing. So I don't know if the video is still something that you can see, but you can imagine on the images in just 2 years, the rate of AI progress at which you can make videos from a pure prompt has significantly gotten better. And this is something that we call the Will Smith eating spaghetti benchmark. It's not as rigorous, but it shows a good example of how much progress AI has made in the last 2 years. A bit more technical is this benchmark which I personally like is creating an SVG. So SVG is a vector image which is encoded as this particular set of code. And for the people in the audience, when you create an SVG, all you have to do is basically copy paste it in an HTML and it will render this particular image based on this code. Now, the interesting part is the language models are now able to understand the user request and create a pretty coherent SVG of a fairly complex image, right? A pelican riding a bicycle. Imagine yourself drawing that. And you can see in just 6 months, the progress in OpenAI GPT has been tremendous. This makes us confident that the language models are getting better and better in understanding user intent, understanding knowledge base, but also really, really good at coding. And we are leveraging that to connect our internal data sources. So how are we enabling this work with our proprietary set of data and our proprietary set of projects that we work internally? So we are building something called as Vortex. This is Tech at Lilly's offering to the enterprise, where we are enabling hosting, tooling, and also building on top of the best frontier language models, be it from OpenAI, Google, or Anthropic. And we are building tools to enable scientists and software engineers quickly enable applications and tool interface built using these frontier models. So you don't have to worry about confidentiality or use cases around potential information leakages. That is something that we are taking care on the tech side. This Cortex is now this foundation layer that is now used to build application on top of, and everywhere from RAG-based model to agents that we'll get to. Some of the first examples that we tried was using language models as translators. So what we did is we provided language models, documentation, explicit instructions, and 1, 2, 3 concrete examples of an internal code base that we used for substructure search. And we use this to help chemists query a specific molecular entity. So fused rings, different functional groups, number of aromatic bonds, rings. So tomorrow, if a chemist comes in and asks the language model to write a substructure query to find molecules with tertiary amines, heterocycle rings, and heteroatoms, the language model actually understands this query as is, in addition to the typos in this particular query, and generate a fully coherent set of code that can be executed for that particular request. Now, this set of query language is not smarts or smirks that is used by Daylight or RDKit. This is an internal language that we have developed at Lilly using LilyMole over the last 10, 15 years. And it has its set of abstraction, its set of classes. So you can use this as an education tool to understand how to write these codes using your substructure understanding for chemistry, but also, as I'll show in the next couple of slides, can use this to actually execute a substructure search through and through. But for now, the first example of, or a first implementation of language model was as a translator, where we are translating users' requests into a full coherent code. The other example of a language model use was around RAG, where we were using retrieval augmented generation to query documents. And here we were using PubMed abstracts, encoded them into vectors, and enabling it to ask questions. Now, we use this where you are now not worrying about language models hallucinating, or you doing the actual manual work of automatically retrieving yourself, but you're using a question and finding the nearest relevant documents for that question and summarizing that question answer for you based on the relevant papers that you get for that specific question. We are now using this for project meetings, proposal synthesis, and then also patent understanding for different therapeutic areas. We expanded this into an enterprise-wide offering that we call Chat in a Box, where you can now go in, upload your meeting minutes, upload your PDFs, and upload your documents, and then you get a question, you get an answer for your question based on that citation documents, and then it also cites the papers that is using to answer that specific question. So these are all specific implementation of language model as a workflow. We are now combining that into an agent that we call as a language model with tools and context, where language model reasons and decides which tool to use. we are developing something that we're calling as kernel Lilly. So it's a play on kernel Lilly, which is who started Eli Lilly and Company. But kernel Lilly is kind of the central processing unit for everything that goes into a language model that connects different data sources and functions and tools and software. So we are using kernel Lilly as a way of having a frontier AI model. We have access to tools, but also an orchestration layer that can connect different processes across different functional areas. So a quick example of a kernel Lilly implementation is enabling web search. So you getting worried about what kind of data is sent out, we are enabling web search as a simple tool call where you can now ask red data or internal confidential data questions directly through this portal. And the kernel Lilly framework understand what is the question that is asked, selects the right set of tools, does the web scraping for you, and gives you the answer based on your question. And this all happens within one application. As a part of this effort, we are connecting kernel Lilly to different data sources, tools, and even other language models that we have developed internally, like I showed the PubMed chat or the chat in the box interface, but also outside world. For example, the Lilly Now or vendor content search that we're enabling through our integration under the Reaxys building block connections. So these kind of API connections is something that we are heavily investing in, where we are now able to connect a language model and give it appropriate context, memory, and also enable it to plan a workflow based on the user request. So coming back to the previous example around a language model translating a substructure query, this was where you are using a query to translate into a full-blown software code. Now you can imagine this connected to kernel Lilly, where you are querying for a molecule in Indianapolis Tube Store that we maintain internally. Now, instead of you writing the code, going to your colleague, searching for it, looking through an inventory database, we can do this process through and through by a pure request, where this is a question that is asked by the user in kernel Lilly, where the kernel Lilly understands that this is a document to be looked up. So Indie Tube Store is the inventory to be looked up. These are the substructures that we want to look up. So first, it looks at the query, translates it into the code, waits for a user feedback to be executed on the substructure search, and it searches the internal database to search for molecules that meet that criteria. And it comes back with the right set of molecules. And we have the ability of sending that as an email to the relevant user, but also to the sample management in charge to start the actual sample management procurement process. This is all done within one application by asking it by a prompt. So you can imagine going from a prompt to an action, it takes one instance where the language model is available, connected with all the available data sources, tools, and the right context. The other application which Nathan and my team developed was around archive filtering, which is actually a pretty interesting application where you have a multiple different papers that are published every month, every week. And what we are doing is we are actually querying that API on bioarchive, chem archive to actually find the relevant preprints based on the user context. And it gives a nice short summary for easy review. And we update that either through in-application message, but also as a specific update on the website if needed. But this is all done by the language model's understanding of the context in which the question is asked. In this particular case, it's actually a multi-agent system where one agent understands the user request and then sends it across to two other agents which do the summarization and the document lookup for you. As we build these capabilities around language models, connect different tools, what we're also trying to do is connect not only the in silico aspects, but also connect it with our lab automation equipments. So we are investing in processes where we can use our internal automation tools like reaction condition screening, protein production, and cloning to be connected with this language model, where you can now query and capture data, but also design and run experiments to test the hypothesis. And what we are trying to do is build this self-fulfilling loop where the language models are able to understand what the experiment was performed and reason the next set of experiments to be performed based on the result from the past experiment. And we are trying to build this by creating an orchestration layer that understands long context questions, but also can allow document upload, save and resume, but also engage with users with multiple different questions. So not just one question and answer, but a human feedback, if you may say so. Finally, one of the things that we think is important to be looked at is the evaluation of these agents. So you can imagine there is a capability uh, framework where you are enabling an agent what the agent could do, but there's also the reliability where you want a process to be done consistently by an agent. So we are building an internal set of evaluation questions, workflows where you can test the reliability as a function of different models, different orchestration types, and see what is how you can create a most robust set of tools and processes that can allow an agent to operate in the wild. To wrap it up, this was a quick vignette of all the things that we're doing on the chemistry side when it comes to AI, but also the language model work that we are trying to slowly enable that can capture different data sources, tools, and processes and build general purpose AI methods and that are cross-functional, making it easy and simple to capture, find, and query data and slowly drive a predict first culture where you're able to put these complex models online and in hands of chemists and biologists to use pretty seamlessly. And finally, as we build these tools, we are heavily integrating our scientists in drug discovery programs to listen and elicit feedback really, really quickly so that we can act upon it and understand what are the roadblocks and potential bottlenecks to build upon these advancements. With that, thank you so much for listening to this talk, and I'm happy to take questions. Are we waiting for questions or are we doing the next talk? I'm sorry, Jay.
So I think
Let's
it's
hand
really
it over to Jayesh. Go ahead, Jayesh.
Okay, we should move over to JS. My bad.
Thank you very much. No worries. Thank you very much, Pushkar. A fantastic talk. So, moving on then. So, just continuing the theme of enhancing data discoverability by leveraging advanced technology, we have been exploring different ways to improve search within Reaxys. Today, Reaxys serves a varying profile of chemists, dependent on the types of research the scientist is involved in, namely those who are reliant on structure-based searching, text-based, or a combination of the two. And it's critical that the process to get to the most relevant answers is efficient as possible. Now, based on feedback, now we are heavily reliant on feedback in terms of where we focused to make improvements. It was identified that although our text search capability is effective, there is a growing demand for search solutions to reliably understand natural language queries. And after reviewing all the feedback, it was very clear this was an area for us to explore further. Okay. So to set the context, today's text search is a rule-based system for all types of chemistry concepts, which is optimized for reaction and structure searching, leveraging a comprehensive, what's happening here? Oh, there we go. Leveraging a comprehensive taxonomy to ensure chemistry understanding. What we are experimenting with is to enhance the existing text search for document discoverability with vector search technology, which will enable natural language processing, simplify the user experience, and improve the search experience for every type of chemist, whether it be a process chemist, material scientist, or a chemical engineer. So, what is vector search? So, at the heart of vector search is an embeddings model, which is an AI tool that turns text, such as an article, patent, and even your chemistry question, into a list of numbers that captures its meaning. If the model is trained on chemistry text, it understands scientific language even better. For example, if you search for Suzuki coupling, the model creates a vector for your query and can find articles about Suzuki reaction or Suzuki cross coupling, even if those exact words aren't used in your query. This way, you get relevant chemistry results based on meaning, not just matching of keywords. Now, building on this technology, Reaxys Vector Search lets you search the chemistry literature using natural language, just as you would ask a question out loud. The model is trained specifically on chemistry data from Reaxys, so it understands the terminology and context unique to this subject. Now, this approach retrieves more relevant results for your queries, even when you use everyday language or complex scientific concepts. By combining the strengths of both vector search and keyword-based search, Reaxys will ensure you get comprehensive and meaningful answers, helping you find the chemistry information you need faster and more intuitively. So here are a couple of examples of what we've been working on. So a query from a medicinal chemist looking for precedence of TRPV4 antagonists being used specifically for treating cancer pain. With a simple natural language query input, the system can understand the intent and context of the query and point the user to the most relevant reviews focusing on the topic of interest. Simple input, relevant output. Another example from a material scientist exploring alternative cathode materials and its benefits for developing the next generation of lithium-ion batteries. Once again, a natural language query. The user does not have to think about how to input the question. The system understands it and gives the most appropriate, relevant results. So after continuous internal evaluation by our subject matter experts, we found that the model's understanding and ability to return relevant results to be very promising. Based on these results, we built a test site to enable our research community to try it out. We invited chemistry experts to participate in testing Reaxys Vector Search, and the initial feedback has been very encouraging. Participants have noted that the system delivers relevant insights across a wide range of subject areas, making it easier we invited, as I say, chemistry experts to participate in testing Reaxys Vector Search, and their initial feedback has been very encouraging. Participants have noted that the system delivers relevant insights across a wide range of subject areas, making it easier to find the information they need. One expert even commented that it's much better than Google for chemistry research, which is a great sign for our approach. Beta testing is still ongoing. If you'd like to try natural language searching in Reaxys for yourself and help shape its future, please click the link, which I think is being shared in the chat, to join our beta program and share your feedback. So looking beyond Reaxys Vector Search and enhancing our text search capabilities, what else do we have on our radar? So I'll just touch upon this very briefly. So with Reaxys AI-based natural language search, we're moving beyond traditional keyword and rule-based searching to a smarter, vector-driven approach. This not only augments our existing search capabilities, but also provides a much simpler and more intuitive experience for our chemists across all subject areas. Our beta version is available now for you to test and experience these improvements firsthand. Looking forward, we're actively experimenting with AI to enable chemistry-focused summarization. So especially for those very broad topics that you might be interested in and you want to get a quick insight into specific topics, we are looking into summarization around those queries, and natural language querying over structured data associated with reactions, substances, and targets. So essentially being able to ask a natural language query, for example, book-wild Hartwig synthesis with more than 90% yield, published from 2022 to 2025, making it much easier than ever to extract insights from complex chemistry information. So lots and lots of interesting things going on. So with that, I will pause and I'll pass back to Randy.
Thank you, Jayesh. I'd like to welcome back Pushkar to the stage. Clearly, the speed of innovation and quality is improving, and that image of the spaghetti improvement is going to be ingrained in my mind for a long time. So thank you for sharing that, Pushkar. So one question. What benchmarks or evaluation metrics do you find most attractive for assessing the reliability and accuracy of generative chemistry?
Is that for me or Jayesh or?
Yes, Pushkar, here.
Okay. Yeah. So I think that's a good question. Depends on the question we're asking. I don't want to give a non-answer, but generative chemistry is quite hard. What we are trying to do is essentially annotate the tools that we are using to answer a given question and assess the reliability of the agent to select those tools, but also exploring ways of either fine-tuning or having a protocol for that given process or a set of questions. So for a generative chemistry example, what we are trying to do is either rely on the reproducibility of the output from a specific tool, so let's say some Gen AI tool that we're using, but also making sure on the agent side, the agent is rightly selecting the tools with appropriate context. So we are essentially looking at the best performance of the last 50 calls or 70 calls on the same question. And we are trying to monitor that progress over changes in different orchestration layer or models.
Thank you, Pushkar. We actually do have time for another question. With the introduction of AI-based natural language searching in Reaxys, will this technology replace the existing document search? Jayesh, if you could take this one.
Sure. So the goal is to actually enhance the current capabilities, because as I've already mentioned, the current text search capability is very, very powerful. It's utilizing a well-established chemistry taxonomy, which really ensures that you get to appropriate results. The capability that I've just talked about today is to actually enhance that existing capability. So essentially, the current way of searching enhanced with natural language querying. So the user doesn't need to think about which way to search, whether simple individual concepts or a natural language question. They can enter the query in any which way and they get an appropriate relevant result.
Thank you, gentlemen. Thank you for the presentations. To our audience, we'll continue with our final speaker here shortly, and please take a moment to answer the survey. Thank you.
Thank you so much, everyone.
Thank you.